Okay, let's try SP3 from Chapter 9. The question reads, a steel block with a density of 7,800 kilograms per meter cubed is suspended from a string in a beaker of water so that the block is completely submerged but not resting on the bottom. The block is a cube with sides of 3 centimeters. So let's draw that. Physics problem should begin with a picture. So we have a beaker filled with water. So there's water in there. And we have a string. It's a steel block. So we know it's steel. Has a density. So the density of steel is equal to 7,800 kilograms per meter cubed. So that means if you have 1 meter cubed of it, a block, 1 meter on a side evenly, the entire mass would be 7,800 kilograms. Is suspended from a string in a beaker of water so that the block is completely submerged. That's key. The block is completely submerged, but not resting on the bottom. That's key. The block is a cube with sides of 3 centimeters. So let's draw that part over here. It's a cube, 3 centimeters on a side. Each side is 3 centimeters. All right, so part A. What is the volume of the block? Well, volume of a block is equal to length times width times height. So we know each side is 3 centimeters, so convert that to meters, we get 0.03 divided by 100 to get into meters. The length is that, the width is that, and the height is that, or thickness. Oh, meters in there too. So what we have is 3 times 3 times 3 is 27. And then we have how many decimal places? 2, 4, 6. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. Let's just do this better. 0.03 raised to the 3. Put it in sci-fi. You get 2.7 times 10 to the minus 5 meters cubed. Multiply the numbers, and you have to multiply the units, so we get meters cubed. It's a small enough number. It's too many zeros. Let's just put it in scientific notation. Now they want to know what the mass of the block is. The mass of the block. Well, we have to use our old formula. Density is equal to mass over volume. So if we want the mass, we got to multiply both sides by the volume. So mass is equal to density times the volume. The mass of the steel, let's put an ST there. Density of the steel, volume of the steel, mass of the steel block is equal to 7,800 kilograms per meter cubed multiplied by the volume, which we just found out is this number, 2.7 times 10 to the minus fifth meters cubed. Multiplying those two numbers out, what do we get? We get 0.2106. It's mass, so it's kilograms. So that's B, that's A, and let's go on to C. What is the C? What is the weight of the block? Well, we know what weight is. That's equal to mg. Mass we have is here, 0.2106 kilograms times 10 newtons per meter equals 2.106 newtons, right? I'm sorry, not newtons per meter. That would be spring constant. It's newtons per kilogram. So the answer is in newtons. That's the weight of the block. What is the buoyant force acting on the block? I want the buoyant force acting on the block. Okay, so that's D. Weight of the, the buoyant force acting on the block is the weight of the displaced water. It's displacing water. So how much water moves out of the way? Well, for volume, for a block of volume 2.7 times 10 to the minus fifth meters cubed, if that's the volume of the block, then that much water must move out of the way in order to put the block in. So buoyant force is equal to the weight of the displaced fluid. In this case, that's water. So it's equal to the weight of the water that's displaced. So that's equal to the mass of the water times gravity. But the mass of the water displaced, we can use again density formula. So the mass is rho times the volume. So mass is rho times the volume times G. Hopefully you recognize this formula from the lecture. So we plug in. Remember, this is water now, right? Water. So we don't put in the density of the steel. We want to find out what the buoyancy force is. And that's equal to the weight of the water. So it's equal to the density of the water, 1,000 kilograms per meter cubed, times the volume of the water. Well, we discussed that the volume of the water is the same as the volume of the block because the block is entirely submerged. Volume of the block is this number from part A, 2.7 times 10 to the minus fifth meters cubed times G, gravity. 10. It's a little tough writing under this thing. 10 newtons per kilogram. So putting all these numbers together, we get the weight of the water is equal to 1,000 times this times 10. Well, this is 10 to the third. Times 10 is 10 to the fourth. So we multiply that by this number and we should get 0.27 kilograms cancel, meter cubes cancel. I'm left with newtons, which is good because we know newtons is the unit for weight. And then we have E. Part E says, what is the tension in the string needed to hold the block? So the forces on here are we have the weight down, which we just figured out right here, the weight down. We have the buoyancy force up, which we just figured out here. So this is really equal to the buoyancy force. Buoyancy force is the weight of the water that was displaced. And then E, we have, we want the tension in the string. Those are the three forces on this block. So we have, we can use Newton. Sum of the forces is equal to ma. Sum of the forces are tension up plus buoyancy force up. Right? Those are both up. Minus the weight down is equal to ma. But this is stationary. It's just hanging there. So the acceleration is 0. So this is equal to 0. Therefore, the tension is equal to the weight minus the buoyancy force. Plugging those numbers in, we get that this is equal to, well, the weight is right here, 2.106, minus the buoyancy force, 0.27. So the tension in the string is equal to 2.106 minus 0.27 equals 1.836. And the units are newtons because it's a tension. Also, weight's in newtons, buoyancy is in newtons, so tension has to be in newtons. So, that's problem 3.